Okay, let's get started. So it's a pleasure today to have Lam Hui visiting. Lam is going to be with us for 3 days. So Lam got his PhD at MIT. He then moved to Fermilab on his first postdoc. After that, he went to the Institute of Advanced in Bristol, and he's now a professor at Columbia University. And he's going to tell us today about cosmic acceleration and the equivalence principle.
Thank you. Thank you for the invitation. So today I want to tell you about work that I did with my colleague Alberto Nicolas at Columbia and Chris Stubbs at Harvard. And before I start, let me just say one word about equivalence principle, because that tends to mean different things for different people. So let me just say I'm going to use the dumbest possible definition of equivalence principle, which is basically what you would use if you're doing an experiment. Let's say I let two objects fall. Do they fall at the same rate? If they fall at the same rate, then I would say equivalence principle in my language is obeyed. If they don't, then it's violated. That's all I mean. Okay. So here's an outline of the talk. I'll give make some brief remarks about basically long-distance motivation of gravity in general. They have become sort of interesting recently because of the observed acceleration of the universe. People at least hope to explain the acceleration using something other than a cosmological constant, for example, by actually modifying gravity on large scales, on Hubble scales. And I want to just make a brief remark why all the proposals that people have considered, or maybe not quite all of them, most of them, 99% of them, actually in some limits, they all reduce one way or another to some kind of scalar tensor theory. I want to explain to you why. And the reason why I want to explain this is because, in fact, none of the proposed theories are entirely satisfactory. So we don't actually know what would actually a compelling theory, what form exactly it would take. But I would say it's fairly one can say generically you expect some kind of scalar tensor theory, whatever final form it might take, if it is indeed the solution to the problem of cosmic acceleration. And after making that introduction, then I want to talk about basically what is known as screening mechanisms. Whatever scalar that you introduce to your theory that is active and alive on large scales to give you acceleration, it must somehow be screened. Again, this is very generic. You somehow have to screen the scalar so that you don't violate experimental constraints, such as in the solar system. And I'll tell you about two screening mechanisms that we know of. One is known as Chameleon. The other is known as strong coupling or Weinstein. And then the third point is really the main topic of the talk. I want to actually just redo a classic, very old problem. How do objects move in the presence of these screening mechanisms? In particular here, I'm interested in not motion of test particles, very small particles. I'm interested in motions of big objects, like a galaxy or like a star and so on, macroscopic objects. And there we'll see, for one of the screening mechanisms, you expect actually order 1 violation in equivalence principle, meaning the following, that if you actually were able to compare the motion, let's say, of a big galaxy versus a small galaxy, one of them would fall with a rate that is, let's say, a factor of 2 faster than the other. In one of these screening mechanisms. I'll tell you why that's true. And then I'll talk about observational tests, how you might actually look for this effect. If time permits, and it really depends on interest, I would like to talk about some recent work that's actually on an entirely different subject, on the subject of bubble collisions. These are my collaborators, but I might or might not have time, and you might or might not have interest to hear about that. We'll see. We'll see how far we go. So let me start with the first point. And here I'm not going to go through all this the whole list. I just want to give you some flavor of examples people have considered, ways in which people want to modify gravity on large scales in order to give cosmic acceleration. And the point I want to make here is, for a large fraction of these examples, they reduce to some kind of scalar tensor theory. F of R is the simplest because they are just straightforward scalar tensor theories. DGP is a theory that involves an extra dimensions where we live on a brain embedded in extra dimensions, and there it turns out the scalar correspond to basically a brain bending mode. The way the brain is embedded in the extra dimension, the extrinsic curvature if you like, is the scalar, it turns out. From a four-dimensional perspective, there is at least part of that degrees of freedom is a scalar that is here. And so in some limit, in particular in the limit when you look at phenomenon on scale much smaller than the Hubble radius, then it looks like a scalar tensor theory. Massive gravity, again, if you do a Stuck-Over transformation, if you just give graviton a mass, you can also show, because you give it a mass, there are extra polarizations, and of the extra polarization, one of them tends to be the most strongly coupled and involves a scalar. And then there are these ideas that are fairly interesting about degravitation. The term used to mean basically if, for example, if the gravitational constant, rather than being a constant, is actually an operator of some sort, where basically is a low-pass filter of some sort, so that an absolutely homogeneous source like the cosmological constant would gravitate very little. And stuff like here in this room would actually gravitate as usual. And that's one interesting way that people hope would solve maybe the cosmological constant problem. This, again, if you actually apply a Stuck-Over transformation, these theories are actually very much like massive gravity, except the mass is actually an operator rather than a constant. Again, you pull out basically a strongly coupled scalar. And I won't go through the rest, but I want to just make a point that again and again in all these attempts, even though I would say none of them so far are completely successful, in all these attempts to kind of come up with an alternative way to explain cosmic acceleration, they reduce some way or another to some kind of scalar tensor theory. And I just want to make a point that, in fact, this is something we should expect. It's fairly generic.
Could you go back to the extrinsic curvature question mark?
Yes, there is a theory by Gregory Gabardasi. It's kind of like a variation on DGP, where in DGP, if you think about it, it involves basically a four-dimensional Einstein-Hilbert term added to what is basically a bulk five-dimensional Einstein-Hilbert term.
What is extrinsic curvature we're talking about here?
Extrinsic curvature of the brain, how the brain is embedded in extra dimensions.
So the extrinsic curvature, it's a 5D.
It's a 5D extrinsic curvature.
So it's not the usual.
No, exactly. And this is actually fairly recent. Gregory is still working on it. But my understanding is you could also recast it in the limit of looking at phenomenon on scales much smaller than Hubble is again some kind of scalar tensor theory. And I want to just briefly explain why this is so. This just comes up again and again. And it's basically because of a well-known theorem due to Stephen Weinberg, that at low energies or on large scales, a Lorentz invariant theory of a massless spin-2 particle must be GR. There's just no way to escape it. And therefore, if you want to modify gravity on large scales, such as what these theories in the last slide attempt to do, generically, you basically either add new degrees of freedom, for example, the simplest one being a scalar, or you make the graviton massive instead of massless. There, if you apply a Stuck-Over transformation, you can also show you find a strongly coupled scalar, or you violate Lorentz invariance, which would be the more radical option. And a common way to implement that is actually yet by introducing another scalar, which is called the ghost condensate. So
Weinberg's theorem does not preclude lambda. You're generalizing GR to include lambda.
Yes, to include lambda. Yes, lambda is okay. Yes. So some form of scalar tensor theory seems fairly generic in that sense. And I want to make this point because all the examples that I showed in the last slide, none of them are completely successful. So if this line of thought has any merit to it, we do not know what form it will take eventually. And so I want to kind of take the view that, well, let's suppose you do have some kind of scalar tensor theory. what kind of generic predictions can you actually make without knowing the precise, ultimate form for your theory?
What does these two slides mean? This slide says that of the previous slide, all theories are scalar tensor-like? Is that what you're saying?
Yes, some form of scalar tensor theory seems very generic.
So all the ones in the previous slide are scalar tensor theories?
Yes, in some limits. So in the DGP, for example, in the limit that you consider wavelengths much smaller than Hubble, the scalar turns out to be basically the brain bending mode. Basically the way the brain is embedded in the extra dimension is the scalar, it turns out. And it's very well described as a scalar tensor theory in that regime, in the small wavelength regime. Okay, so this kind of...
Always with the normal kinetic piece?
In the case of DGP, it's just normal kinetic piece, although it has very interesting derivative coupling. I'll show you an explicit slide later. The scalar has a normal kinetic piece with interesting derivative interactions. I'll show that.
You're going to, I assume that what this is doing is setting us up to say, therefore, let's just do scalar tensor.
Yes.
But there are all sorts of issues in terms of the coupling to the rest of the matter.
Yes.
Or the scaling, because you're having
Yes.
to do all sorts of conformal transformations.
That's right.
To change the theory. But every time you do that, you're creating interactions that didn't seem to be important in one sector. They become important in the other because that's the way that you're changing the theory. So calling it scalar tensor is probably legally correct, but it's also got a whole matter of sector interaction.
Oh, yes. Oh, yes. That's going to be important. That's actually precisely what I'm going to talk about. So when we come to those explicit examples, we can discuss some more. What are the various variations? Okay, let me just make one more general remark of this sort. In case some of you and some of us do think of modified gravity as, in a sense, a very exotic business, let me just remind you, in some sense, unless you believe the explanation for a certain is just a cosmological constant, if it's some kind of slowly rolling scalar field like quintessence, there's some sense in which modified gravity is no more exotic than quintessence because, absent symmetries, the quintessence should be coupled to matter at gravitational strength. It's kind of basically Dick's point earlier, how it couples to the matter. And in general, you should expect this kind of coupling, just gravitational string coupling. Once you have that, you have scalar tensor theory again. You have to worry about it. Theories of this sort. So in some sense, it's actually not that exotic a phenomenon to consider. Okay, so with all that, let me skip these general slides. So again, not knowing the precise form of the theory, nonetheless, we know we need to impose some requirements on such theory. The requirements being, number one, we want the scalar to have an effect on large scales, meaning we want the scalar to actually modify, for example, the expansion law with actually not a small correction, but actually order 1 correction in order to explain the observed acceleration. So we want the scalar to be, so to speak, alive on large scales. But the scalar must be screened on small scales to match existing constraints from solar system. For example, i.e., the theory must actually, some way or the other, on small scales, match GR fairly well because the constraints are fairly strong from the solar system. And the only 2 known screening mechanisms that we know at the present time, one is called Chameleon. The other is sometimes called strong coupling or Weinstein. I will explain what both of them are briefly in the next slide. Both of them make use of basically the self-interaction of the scalar. Chameleon use basically just a potential self-interactions. Whereas Weinstein use derivative interactions. And let me show you explicitly these examples. Okay, so the next slide is going to be a little bit busy. Let me lead you through it. The Chameleon screening, it was discussed by Justin Curry and Amanda Wellman. And I'm going to discuss both in the Einstein frame, so to speak, where I have this scalar phi, and in both cases, I'm writing out not the full action of the system. I'm actually writing out only the part of the system, the part of the action that has to do with this scalar. I'm leaving out the part that has to do with the metric perturbations. So think of the part that I'm leaving out as basically the Einstein-Hilbert term, if you like. Okay, so there's a part that I'm leaving out, which involves the metric. The scalar sector looks like this. You have a kinetic term, you have a potential for the scalar field, and in the red line here I show you a potential. Usually it's a runaway potential of this sort. Why this particular shape you'll see in a moment. And then most importantly is this coupling that Dick was referring to. There's a coupling between the matter T mu nu, basically is traced with the scalar, with some coupling constant I will just call alpha here. And generically, alpha is order 1. In case you're wondering here, I'm setting basically, I'm almost always setting m Planck to 1. But later on when we actually discuss the astrophysics explanations, then I'll put back in m Planck. So alpha equals 1 basically means gravitational strength coupling. And as I said, this is in Einstein frame, basically meaning the gravity part of the action is exactly Einstein. It's just Einstein-Hilbert action. And then matter, in addition to being coupled to that metric, is also coupled to the scalar field.
It looks like alpha has units of mass to the -1.
Again, put in appropriate units of m Planck to make the dimensions work out.
So the Curie and company modified this, and they made alpha a function of matter type in order to try and actually satisfy the solar system constraints, which of course took
Matter
away
type.
the
Right.
dilettante picture. So
I don't think that's necessary, as far as I know. That you say,
well, I don't know why they did it.
Right.
They did it. Well, I do know why they did it.
Yes.
They did it because the simple dilettante theory didn't work, and in order to try and do
I
what
see.
they wanted to do.
I see.
So,
It probably depends on the potential you choose. I don't know. If you choose, I believe if you choose the right potential, so the idea is roughly the following, right? So you have this potential. Phi obeys an equation of motion, which is box phi equals the derivative of the potential plus a term, which is basically
I mean, you're
rho.
right, because you could use V to pin phi.
Yes.
I mean, you know.
Yes. So it's
But then you are trying to solve another problem.
yes.
They were trying to solve a problem, which was lambda.
Yeah, if you are more demanding on your theory and want to use potential for phi that are more or less well motivated, I think you might have problems. But if you allow yourself the freedom to choose potentials, then I think you are probably okay. You don't have to violate.
Yeah, okay. Anyway, go ahead. Just pointing out that Chameleon became multicolored.
Yes. So let me explain the mechanism, how it works, right? So phi effectively sees the original potential plus a potential that depends on basically the rho, the matter density. Here, basically, I'm approximating the trace of T mu nu by rho, assuming it's a non-relativistic matter. And so you can see, because of this linear coupling, effectively phi see a potential that's linear with a slope that's determined by the local density rho. And so the effective potential is basically the sum of the red line and the blue line. And here you can see how Chameleon works, right? If you are in an environment with small density, then this blue line has very shallow slope. Therefore, the field would like to sit at a minimum, local minimum, that has a large expectation value and a small mass. And so the scalar field, for example, at cosmic mean density, could, in principle, have long Compton wavelength. Whereas if you look at a local density, like basically inside the Milky Way or in the solar system, the blue line has a very steep slope, maybe something like this here. And so the minimum actually gets shifted to a very small expectation value for phi and a very large mass for phi. And therefore, phi have a very small Compton wavelength. And if you make it sufficiently small, you can evade solar system tests. Just make basically your scalar very short range in a high density environment. And that's why the term Chameleon is appropriate, that the scalar field has a mass that actually depends on environment. So that's how Chameleon works. But back to Dick's point, I think you are pointing out something important here. You know, if you look at the current theories like f of r and so on that attempt to explain cosmic acceleration, in the end, if you actually look at what they do, it amounts to actually choosing a potential that actually has a cosmological constant. So in fact, these theories are not even explaining cosmic acceleration using anything genuinely new, so to speak, or modifying gravity. So that's the sense in which I said all these theories are not very satisfactory. But again, the main point I want to make is the following. Suppose this line of thought is correct. Some form of scalar tensor theory is something that we should pay attention to. Then you have to use one or the other as your screening mechanism, as far as we know.
You rule out these theories by the integrated Sachs-Wolf effect of models?
Rule out which theory?
Because you would have order one multiplication of them and then show to draw the same events, right?
Yes. Yes. Then it really depends on the exact theory. And in fact, with f of r, usually, at least the way people choose it, the f of r doesn't even have very long content wavelength, which basically means the f of r effect, the ISW effect is actually fairly small for those theories. So those theories are not even generally modifying gravity on Hubble scale. This might be a better case, I would say, in my mind, a more beautiful way of doing, basically implementing this idea. This actually does have order 1 effect on the ISW effect. And in fact, that actually creates a bit of tension for DGP just from the ISW because it actually over-predicts the ISW. In fact, it predicts CMB, for example, temperature and isotropy. The C sub L at low quadrupole, it exacerbates the low quadrupole problem in the case of DGP, actually. So you're right. So let me actually talk about this mechanism, which in my view is probably is somewhat more appealing. So if you compare this action with that action, everything is the same except what I underline in red. So instead of a potential, you don't add a potential here. You add basically derivative interactions of this sort, where m here plays the role in some sense. In fact, it's in a sense that it can be made very precise, actually some kind of graviton mass. And if you look at this theory, if you write down the equation of motion, you have the usual box phi, but then you have these funny, kind of unusual stuff which involves second derivatives to some higher power. But notice no higher derivatives though. No third derivatives, no fourth derivatives. That's actually what makes these theories somewhat interesting, because if you have higher time derivatives, you have problems with those. These, at least at this level, doesn't. Okay? Now, what does this term do for you? Well, you can basically imagine the following. Suppose you have a source, which is a point source, a rho m here, a point source. Suppose you are very far away from the source. If you're very far away, you can convince yourself basically box phi dominates, and you can solve for the profile of phi around your point source, and it's the usual 1 over r. We are basically making the quasi-static approximation. So ignore time derivatives. This is just Laplacian of phi equals rho, and if you have a point mass, it's 1 over r. But when you get sufficiently close to the point source, these terms becomes important. These terms that involve second derivative to higher power, they becomes important. And you can do just dimensional analysis, more or less, to convince yourself these terms could actually turn this 1 over r behavior for phi at large distance to become square root of r at small distance. And that's what suppresses the scalar at short distance. So that's known as the Weinstein mechanism. Or
if you're in a regime where that high derivative term is important, then don't you need to include other ones like 1 over m4 corrections?
Excellent, excellent. You can actually show that that these terms actually have special symmetry that protect them, and the symmetry is called Galilean symmetry. It's the analog of shift symmetry, except that it's more than shift symmetry. It's shift symmetry on the scalar field phi. Obviously, it has stat symmetry because it only involves derivatives. But because of this structure, you can show it actually there's a shift symmetry even on basically the derivatives of phi, and that actually only limit the terms to actually a few different combinations. And in the case of DGP, it can be shown explicitly with this higher dimensional setup. You can show in the case of DGP, you actually reduce exactly to this term.
So to the mu phi, I can add a constant vector, are you saying?
Yes, that's the Galilean symmetry. So it was explained very nicely in a paper by my colleague Alberto Nicolis and Rattasi. So let me just recap. So the key in both cases is some kind of nonlinear self-interaction with the scalar field. One involves the potential, one involves the derivatives.
So is that, are you actually starting with the massive graviton? I mean, when you call it the graviton mass, is it a long wavelength concept, or is it actually a mass which is universal?
Yeah, it's actually a mass that's universal. So here's the way you might see it. So if you have
and what's its value?
Sorry?
What's its value?
Hubble. You choose to be Hubble. So that's some fine tuning here. You choose it to be Hubble in order to.
It isn't driving to be Hubble. It's assumed to be current Hubble.
It's assumed to be current Hubble. Yes, it's an assumption. And in the case of the DGP setup, that assumed Hubble comes from a combination of the 5-dimensional Planck mass and the 4-dimensional Planck mass. That combination is chosen to have a small parameter, which is the current Hubble. Yes. On the issue of the graviton mass. So basically, if you look at
Only a small fraction can see you.
Only a small fraction?
Yes, we have an opening angle which doesn't quite work.
Should I do it here?
Yeah.
So if you look at the equation for h mu nu, so this is something I'm going to do later, actually. So I might as well write this out explicitly. If you take a metric, you expand around Minkowski. So this is Minkowski. This is your metric perturbation. At the level of the linearized equation of motion, the graviton mass is something like the following. Yeah. So the second derivative acting on h mu nu is of course involves some tensor contractions, which I'm not writing out explicitly as this term, but then the mass term is something like this. It turns out you can actually show that by basically making the following substitution, plus 5, for example, you can actually, if by doing this at the level of, let's say, the action, you can isolate the part of the scalar that is most strongly coupled when you take the limit m become very small. And that, if once you do that, you would get something like this in the case of DGP. Although, yeah, it's not supposed to be entirely obvious. But this is basically a Stackelberg transformation on the h mu nu. I can explain it some more later if you wish. Thank you. Thanks. Okay, so let me come to the main part of my talk, right? How do objects actually move under these two screening mechanisms? Again, these are the only two screening mechanisms that we know at the moment. There could be more, but at the moment there are these two. Let me give you the naive answer. So one would think the answer would be very simple, right? How do any objects move in these theories? Well, you have a scalar tensor theory, then just transform to Jordan frame. And all more objects, you just move on geodesic in Jordan frame, right? That would be the naive answer. Because in the Jordan frame, the matter is minimally coupled to the metric. Here's what I mean. So this is the Einstein frame. And this, I'm writing only the part of the action that has to do with matter T mu nu. And this term, phi multiplied by basically T mu nu is precisely the scalar matter coupling that I wrote down earlier in the last slide. If in the last slide I had included the metric part of the action, there should be a coupling of the matter to the metric, which I call h mu nu here. And more precisely is the metric perturbation. So this is the Einstein frame metric. And clearly I can combine these two terms and relabel the whole thing as h mu nu tilde. That is precisely what people call the Jordan frame metric. And the transformation from here to here is nothing other than a conformal transformation. And once you do this, it seems your matter, since it's minimally coupled to this Jordan frame metric, then it seems it's a no-brainer, right? Any object should just move on geodesics of this metric, no?
How do you suppress the alpha?
Sorry?
How does the alpha get suppressed if h mu nu looks like how you define it?
Yeah, I'm just writing this is equal to this. So
oh, it's not the h tilde mu nu over there. It's not the d mu.
No. Oh, I'm sorry. I'm sorry. Yeah, this has nothing to do with that. This. Yeah.
Sorry, don't worry. It's just.
Yeah, sorry. Let me call this star or something. Yeah, sorry. So if you like g mu nu tilde is e to the alpha phi, something like that. It's a conformal transformation. So except I would say not so fast. Actually, the idea that any object, including especially macroscopic objects, move on the Jordan frame metric is actually not true. That's what I want to show you. And let me remind you one thing, which has nothing to do with general relativity, nothing to do with scalar tensor theory. It's just Newtonian gravity even. Even in Newtonian gravity, let me remind you, extended objects, i.e. macroscopic objects, they do not necessarily move like test particles, even in Newtonian gravity. And just because of tides, right? Because, for example, if you look up Newton's Principia and you want to find the discussions of the motion of the Earth around the sun, you actually spend a lot of time justifying why the Earth's motion can be well approximated by that of a test particle, as if the Earth's macroscopic structure doesn't matter. And there's a very, very good reason, right? Because if you work out the effect of tides, i.e. if you ask what is the scale on which the sun's gravitational field vary, that's a lot bigger than the dimension of the Earth, and therefore this is negligible effect. It's no tides. So, let me just remind you, even Newtonian gravity is something that you have to think a little bit about. How do macroscopic objects move? In the rest of my talk, I'm going to make the same small tide, zero tide approximation. I'm not considering tidal effects. It's not tidal effects that I'm talking about. Okay? So what am I actually talking about? I'm going to give you an intuitive reasoning, and then I'll tell you how you might actually want to justify what I'm saying on a technical level. Okay? And the argument is simplest in Einstein frame, actually, where, let me remind you, the matter part of the action, T mu nu, is coupled to both the scalar field and the metric. Yeah? In other words, in Einstein frame, the scalar literally mediates an actual fifth force between, let's say, two different matter particles or two different objects. And let me make an important remark here is that when you write the action this way, explicitly your scalar is universally coupled to everything, all forms of T mu nu, the way I'm writing it. I.e., I'm not considering theories where alpha, kind of the example they gave, that alpha actually vary from one particle species to another. That's not what I'm talking about. It's universally coupled. And so at the level of the microscopic action, there doesn't seem to be any apparent sources of equivalence principle violation. Okay? There are, of course, a lot of papers in the literature actually talks about exactly equivalence principle violation coming from a coupling constant that depends on the particle species. That's not what I'm talking about. Okay? Let's think about how macroscopic objects interact with the scalar. One way to think about it is basically this part of the action. You can think of it as basically some coupling constant times basically the scalar charge Q of the object, which is nothing other than an integral of the trace of T mu nu multiplied by basically the whirl line action of the scalar field. And once you actually think of it this way, there is actually a well-known effect that violates equivalence principle for scalar tensor theory, and it's been known for a long time. In fact, there's a name attached to it. It's called the Nordtvedt effect. And I want to mention it because this is also not what I'm talking about. But let me just emphasize, tell you a little bit about what this is, because it's a little bit related but not exactly the same. If you look at a regular star, let's say, like the sun, you can ask the question, what is the charge to mass ratio of an object like the sun? And you would find basically the ratio is very close to 1, right? Because for a non-relativistic system, this is nothing other than rho, and so you integrate the volume, that gives you actually the mass also. So the charge to mass ratio is very close to 1. And now consider the opposite situation of a very relativistic object. For example, a black hole. Consider a black hole. A black hole, in fact, has 0 T mu nu, right? A black hole has a mass that comes entirely from its gravitational self-binding energy, entirely from basically this very nonlinear gravitational field. And therefore, its scalar charge is actually 0. This is saying nothing other than what you know as the no-hair theorem. Black hole has no scalar hair, and therefore black hole has charge to mass ratio of 0. And so if you can actually do an experiment and let a black hole and a star like the sun actually fall under the same external gravitational field, they would fall at different rates. And the difference will not even be small. It will be order 1. Yeah? So that is also well known, I should say. And it's called the Nobel effect. That has been known for a long time also. Okay? So let me amplify the last point a little bit. If you think about this in the framework of a post-Newtonian expansion.
Just,
yeah.
Okay, so you're trying to be generic, but let's just be more specific.
Yes.
So let's take a star just before it collapses to a black hole.
Okay.
So it's got, and let's make it spherically symmetric, and so it's got what you're saying is that it's got a phi field
yes.
that is responding to whatever equation you've decided that you're
yes.
going to go with.
Yes.
The scalar tensor.
Yes.
And then, are you telling me that it suddenly disappears? And how does it disappear?
The scalar charge is not conserved.
No, but what happens to the field? Does it radiate? Does it get sucked in? Probably sucked in.
Does it radiate the field? That's a good question. So,
radial radiation is a rather exotic thing, but I guess not.
But it's scalar. It's not.
No, it's exotic, it's not, but it's
right.
possible, sure.
Scale, yeah, it does allow monopole radiation because it's a scalar.
I mean, it must be a continuous process
yes.
in making this transformation.
Yes, yes.
So something happens.
Yeah, if you let a star like the sun, which has charge to mass ratio of 1, and it collapses, I would say it's actually radiated away, but I have to think about it. I would say it's radiated.
It might be an interesting calculation to do. He's here. He's not here.
It might even have been done. I'm not.
Well, not within the context of scalar tensor. Usually the scalar is just minimum couple.
Right.
Because there are those theorems that say that a black hole cannot have a scalar hair, so it should be related to. So
that's what you're saying, but it's
yes.
also possible that as you get towards the Schwarzschild radius, maybe the field is becoming tighter and tighter, and then it's sucked up into the
inside the horizon.
South, who knows?
Yes.
So, it
yes.
require more careful study.
Yeah, my understanding is, let's say you don't actually consider all the way to a black hole. Let's say it's just to something very compact, a neutron star or something. Yeah. I believe a neutron star already have suppressed charge to mass ratio, which suggests to me that it's not sucking in the scalar field. It's rather you're really just radiating away. I know if you consider neutron star, it already have suppressed charge to mass ratio. And it turns out the important point is actually this one that I was trying to make.
Volume average trace T.
Yes. It's becoming very relativistic, right? So, and you're looking at the trace.
Ultimately, the pressure does become significant. But,
exactly. So it's a matter of how.
Is it actually the term that's making a big modification? It's making some modification. Yeah, maybe.
It's an interesting question. But the point I wanted to make was, if you think about this effect in the framework of a post-Newtonian expansion, the effect that the not bad effect is kind of like an order 1 over c squared effect in the following sense. If I compare a regular star like the sun and the Earth, they are going to have the same charge to mass ratio, basically 1. You will only see a large effect if you are comparing a very compact object like a black hole or neutron star with the sun. And in other words, the departure of the charge to mass ratio from 1 is roughly given by the fraction of the mass that comes from gravitational binding energy. And so this is kind of like a relativistic effect, if you like. It's a 1/c² effect. Now, what I want to tell you about in the case of chameleon screening is not an order 1/c² effect. In fact, it's a Newtonian effect. It's order 1. It's not relativistic. So that's the point I want to emphasize. And here's the way to think about it. Let's see. Let me start on the right with an object that is fairly dense, and therefore you have chameleon screening. And on the right, you have an object that is actually kind of not very dense, and therefore you don't have chameleon screening. What do I mean by that? It means the following. On the right, you have an object whose density is not sufficiently high, or actually, if I want to say this more carefully, it's the gravitational potential. The potential is not sufficiently deep, that the scalar field is trapped at some small depth, and therefore the scalar field throughout from outside to inside that object always has a small scalar mass, and therefore the scalar field is always long range throughout. This is what I call an unscreened object. In other words, in this object, there's no chameleon screening. Whereas this object has a deep gravitational potential, and it does have chameleon screening. What does that mean? It means outside, the scalar field has small mass, but inside it has a large mass, short range. And because it has a large mass, it means anything interior to the object would not contribute to the scalar field outside because it's very Yukawa suppressed. There's a very strong Yukawa suppression. In other words, if you want to calculate, let's say you're an observer here, and you want to ask, well, what is the field that I'm seeing being sourced by this object? You are going to conclude only a very small fraction of the mass of this object would actually source the scalar charge, because anything interior to this object would not contribute to a field profile outside, because again it's Yukawa suppressed. Only a very thin layer, people call it a thin shell, with a thickness of the order of Compton wavelength, would actually contribute to the scalar that is observed outside. And therefore this screen object has charge to mass ratio that actually goes to 0. In the limit, this thin shell becomes very thin. It's just basically Yukawa suppression. And so this effect is entirely Newtonian in the sense that this have small charge to mass ratio, this have unity charge to mass ratio, and the only deciding factor is the competition between two things. One is the depth of the gravitational potential well. The other is more or less basically the scalar field value outside, divided by, this is just the coupling that's generically order 1, alpha. It's basically competition between the scalar field value outside and the depth of the potential, if you just work out the chameleon equations. And so depending on the choice of the parameter in your theory, even potentials that are not very deep could exhibit this effect. In fact, because we want the Milky Way to be screened, you basically want the scalar field outside to be basically something like 10 to the minus 6 or so, because the gravitational potential of the Milky Way is something like 10 to the minus 6. It's V/c². Okay, so let me conclude this part, which is really the main part of what I want to say, is screen and unscreened objects have order 1 difference in their charge to mass ratio. Therefore, they would exhibit order 1 equivalence principle violation, because again, in the same external gravitational field, the unscreened object would see the full scalar force, would experience the full scalar force. A screened object would not see the scalar force at all. It basically doesn't couple. It has very small charge. Therefore, if the scalar field is coupled to both at gravitational strength, there would be order 1 difference in the rate at which they fall for a screened and an unscreened object. And this effect is Newtonian. Another way to say is basically your scalar charge is being renormalized by basically the chameleon mechanism.
But it's phi that matters, though, not the density. I mean, like.
It turns out it's phi.
So
it's not rho.
Stars in a small galaxy.
Yes.
The escape velocity against those stars is deep enough.
Yes.
But then the stars themselves are all screened.
That's right. So
even the galaxy itself is very, very shallow.
Exactly right. It turns out for the Milky Way has a potential that's roughly the same as the potential of the sun, roughly, to within order of the field, 10 to the minus 6. But for dwarf galaxies, let's say, then the galaxy as a whole is not screened, but the star is screened. Because the star is always like the sun. It depends on the kind of star you have. But if you look at just a main sequence star, it turns out the mass to radius ratio is roughly constant, roughly. And so they have actually roughly the same potential for main sequence stars. But you talk about red giants and so on. Okay, so this is kind of the main point. I'm not going to go through these details. This is kind of derive exactly why is the potential that matters. I think I'm going to skip this part. And let me just say a word about how we actually put this on firmer footing by actually deriving this at a technical level instead of just relying on these intuitive arguments. And here's how you actually derive basically motion of extended objects. It's basically, it was a trick actually introduced by Einstein and collaborators. We learned it from a very nice article by Moore. Basically, the idea is, let's say you have some object M with mass M. You draw some surface around it. It doesn't have to be a sphere, any surface S. The momentum of this object is, of course, just the volume integral of Ti0, where T is the energy momentum. And in this case, I'm choosing it to be the pseudo-energy momentum for reasons that you see in a second. If I look at the time derivative of the momentum, then you can see you induce just conservation on Ti0 to convert it into basically a divergence. And then you can reduce basically the rate of change of momentum on the object into a surface integral of the momentum flux. It's nothing extraordinary. It's something you expect. The momentum flux through this surface gives you the rate of change of momentum. This trick is very nice because you can always choose your surface to be sufficiently far away from the object so that your metric perturbation is small in spite of the fact that your object might be a black hole. And therefore, you can actually work out how objects move. And because you only care about the momentum flux at the surface, you also do not care about self-forces inside the object, which is always a confusing question when you think about motion of the object. And you can do this equally well in Einstein frame and Jordan frame, and you can show the answer agree, which means the following. In Jordan frame, it's not true that all objects move on geodesics. Some object, i.e. the unscreened object, would move on Jordan frame geodesic, but the screened object actually would not move on Jordan frame geodesic, based on the reasoning I gave you before. But you can make this fairly rigorous by basically doing this kind of calculation. I'm going to skip this. Let me give you a summary. And this is a Jordan frame summary, because that's the frame we often use. So the mass, you have an object of mass m times the acceleration of that object is, of course, given by the mass times gradient of the external gravitational potential. That's the usual answer, except now here is modified by this factor in the bracket. And this factor involves two numbers. One is epsilon. It basically describes the amount of screening. And here I choose epsilon to be 1 for an unscreened objects and 0 for screened objects. Yeah? So epsilon is kind of like the charge to mass ratio, if you like. And then alpha is, again, this scalar matter coupling, which is generically order 1. And what this factor tells you is that if you have an unscreened object, then the numerator and the denominator just cancel to give you 1, and you get the usual answer that you expect in Newtonian gravity or GR, which is that gravitational mass, which is basically this mass, is equal to the inertial mass. But if epsilon is 0, you will find the gravitational mass is different from the inertial mass. And again, if alpha is order 1, generically the difference is order 1. Let me give you an example. F of r, for example, has alpha this particular value, 1/6, where so that the unscreened to screened gravitational mass is basically a factor of 4/3 for f of r. Although I should emphasize again, f of r is actually not a particularly, in some sense, not particularly natural theory. this very special value for alpha, for the coupling, is not protected against quantum corrections. I think one should just say, generically, you expect alpha to be order 1. And so in these theories, Chameleon theories, the two important parameters is alpha, the coupling, and the scalar field value at cosmic mean density. Because it's the scalar field value competing against the gravitational potential of the object that determines whether it's unscreened or screened. So these are the two parameters. They are important in these theories. For Chameleon theories, let me just say a word about Weinstein. This I will be very brief. It turns out for Weinstein, it's actually in some sense much more robust, that you are really protected against these violent equivalence principle violations. And the reason actually is actually very simple. It turns out the equation of motion for your scalar field can always be written in the Gauss law form, i.e. rho is equal to the divergence of some current. And because it has some Gauss law form, basically it means you always have the scalar charge that is conserved and is protected against basically this kind of chameleon-like renormalization of the scalar charge. And therefore, if you do the calculations, there's no such Newtonian order 1 violation of equivalence principle. However, with the Weinstein mechanism, you still would have the not-red effect, meaning, black holes and regular star would fall at rates that are significantly different. With Weinstein, that effect is still there. That relativistic is still there. But the non-relativistic effect is gone, basically. There's no chameleon-like violation of the equivalence principle. This is just a summary. Yeah, this is the same slide I showed you before, except that I added this remark about the Milky Way and the Sun having gravitational potential in -6. And so the observational situation looks something like this. In this chameleon-like theory, where you have two parameters, the scalar matter coupling and the scalar field value. If the scalar matter coupling is very small, you can see there should be no constraint, right? You have a scalar that's just not coupled to anything. Of course, you cannot say anything. If it's sufficiently strong, if alpha is sufficiently large, then you can say something basically out here is ruled out. Because if you are actually living at a point here, you would say Milky Way or the Sun should be unscreened, and therefore you have large violation of GR. So this part is ruled out, basically, out here. And if you think of this as a parameter game, what you want to do is to push your curve to something like here. And let me just briefly talk about the possible observational tests. And the idea, of course, is to replicate this classic experiment supposedly done by Galileo, where you drop two different things and compare the rate at which they fall. And I divide the tests into bulk motion tests, meaning I'm going to use in these two tests basically galaxies as a whole, the motion of galaxies as a whole as the thing that I want to measure. And internal motion tests where I am kind of following kind of a Niels idea, which is I'm studying basically motion of objects within a galaxy. So what I call internal motion tests. Let me not talk about all of them. Let me just talk about, for example, the first one, right? If what I'm saying is correct, if you have a theory with the right choice for your parameters, it could well be that a small galaxy like a dwarf galaxy is unscreened, whereas a big galaxy like the Milky Way or a more massive is screened. And so if you have somehow find a way to compare the relative motion, they are going to fall at different rates. It's the equivalence of having some kind of velocity bias, if you like. And as you know, this is something that, on very large scales, the implicit assumption of a lot of us working in large scale structure is that there's no velocity bias, that all objects basically trace the same velocity field. If this effect is there, then it will violate that assumption, and one has to be careful. Although that's one caveat that we have to be aware of. Let me talk about that in a second. Let me jump to a version of the internal motion test, and I think this is actually probably the most robust, actually, which is look for a galaxy, a dwarf galaxy like what Neil mentioned, that is unscreened. Now, measure the rotation curves using two different traces. One is hydrogen gas, which is very diffuse and therefore unscreened. And the other is use stars, which is sufficiently compact that they are screened. And therefore, you should find inconsistent rotation curves. That if you find the right galaxy, you will find that the rotation curves V as a function of R will look something like that, maybe. Yeah, that hydrogen gas being unscreened would fall at faster rates, i.e. it sees a higher Newton's constant, if you like, compared to the star. Exactly how much, what's the difference, depends on alpha, the scalar matter coupling. But I should also emphasize, in all these cases, there are at least some caveats that one has to keep in mind in doing this test. Number one is that observationally people know, actually, when you actually do this measurement, they are inconsistent. There's an effect called asymmetric drift. So you have to be careful about that. Number two, which is also important, is you have to avoid situations where you have blanket screening. We call it blanket screening. And it's basically the following. If you study, let's say, a dwarf galaxy, if you look at a dwarf galaxy sitting inside a cluster, then because the environment has such a deep potential, the dwarf galaxy would be screened. And therefore, everything inside is also screened. So if you look at dwarf galaxy in that environment, you won't be able to see this. You have to look for basically objects that are relatively isolated from everything else. So you have to be careful. So there are caveats.
What happens
yes.
when you have hydrogen gas that collapses so close to unscreened to screen?
Very nice.
What happens to the angle then?
Yeah, that's a very good question. In fact, if you think about stars, we know form from collapse of this diffuse gas. So at some point, this object, this gas cloud, go from being unscreened to screen. So suddenly it sees a much smaller, if you like, effect of two smaller Newton's constant. And so the object is going to move around in the galaxy. And this is something I've been discussing with David Hawk at NYU. Basically, your star should actually move out, no? Because you'll be seeing basically a smaller Newton's constant. So after you collapse out from the gas cloud, your star should move out. And if you choose actually the right galaxy where there is some radius within which everything is green and external to it everything is unscreened, this kind of dynamics could create a gap in the stars actually. And it's something potentially you could look for and rule out these theories of the constraints. I'm not sure, is that what you're asking?
Yeah, basically. I'm not sure if
yes.
you create a gap, but you create velocity dispersion.
You would create velocity dispersion as well, exactly. You would create, let's say you have clouds that is completely organized motion, completely circular. This effect would create actually radial basically oscillations, if you like. Yes, absolutely. So I suspect there are a lot of things that could be worked out. Some of these effects might be sufficiently large. We can already rule out a large fraction of the parameter space. I think I'm running out of time. So I wanted to talk about bubble collisions, but I don't think I have time. So I'll tell you about it in private if you are interested. I'll end my talk here.
Okay, any more questions?
Okay, so let's go back to step 0. So there is a dynamics associated with the expanding universe.
Yes.
In which the phi dot dots can become relevant.
Yes.
Is there anything amusing coming from that? Or is that just like a quintessence evolution?
There is. Depends on the theory. In this theory that you kind of cure all problems by adding a potential, then there's nothing interesting. But in this theory that cure these problems, for example, screening by adding derivative interactions, there are actually interesting effects. So
you don't have to go through the details because we'll go through this later over
sure.
coffee.
Sure.
Okay, so that was one class. So you're saying that
yes.
in fact you can make interesting modifications to the usual evolution associated with this.
Yes.
And then the other regime is, and maybe this sort of belies it,
Yes.
just as with gravitational perturbations with an appropriate nonlinear longitudinal gauge,
Yeah, yeah.
you can then reduce things to effectively the Poisson-Newton equation on the gravitational sector.
Right.
Here, there's going to be some fine modification to that, and
Yeah.
that's coupled into an equivalent, essentially Poisson equation with either a very complicated, gradients, Laplacians to these extra powers that are modifying. So really what we're dealing with, and this is a question, it seems like at some level what you're dealing with is two simple Poisson equations that should be describing things, and what you're trying to do is to be agnostic on the form of V or on the form of the explicit form of the graviton that you're putting in,
Yes.
so that you've got the discussions of screen and unscreen. But to me, the whole issues are exactly how the transitions go,
Yes.
because the transitions are going to have a characteristic scale, which
Yes.
means that if you're going to solve one problem on one scale, you aren't going to solve it on the other.
Right.
It can't
Right.
be all things to all people, as
Yes.
it were. So
Yes.
there's a lot to be said for doing simple things with explicit parameters as opposed to trying
I
just
agree.
to do the two limits.
I agree. I agree.
But is it as simple as that you're just doing another gravitational, another potential calculation for your script, verify or whatever it is, as opposed to
Your scalar.
capital Phi?
Yes, yes.
So it would actually be pretty simple to do and body and all that with this stuff.
Yes, that's correct. That's correct. That's exactly right. And in fact, there are n-body simulations of actually both the Weinstein case and the Chameleon case, where what they do is they take an n-body code, and in addition, they solve an extra scalar equation. And the scalar and the gradient potential basically tells you how objects move.
Because what I would like to see are things like, okay, so you're going to fool around with the interiors of galaxies, therefore you're going to have a huge impact on clusters.
Yes.
And the issue is that okay by the observables or not? And that's just one example of the many that it would have impact on, because if you're going to do a galaxy modification, then you're probably going to get the asymptotic modifications on all larger scales.
Yes, yes. Are you talking about back reaction of small scale stuff on large scale stuff?
No, I'm basically talking about that essentially a cluster would be an unscreened environment.
A cluster would actually, in the Chameleon theory, it would be screened.
Something on galaxy scale.
Yes. A cluster would actually be screened because it's fairly deep. I mean, a cluster has deeper gravitational potential than the Milky Way.
Parameters you put in to try and you qualify it.
Right, right, right.
You're putting in some potential
Yes.
in order to have a self-interaction which is significant, as well
Yes.
as the coupling to TM.
Yes, yes.
Right, and so there's a lot of art in that.
Yes.
There's scales in that, and what you do will make a very big difference on what the response is.
Sure, sure, sure. Yeah, so if you want to actually do what I said here, which is basically looking at just motion of objects on small scales, and at the same time, you want to actually see if your theory is capable of also explaining the cosmic acceleration and the large scale structure data, then clearly you need actually specifics. You need actually a specific model. The unfortunate thing is at the moment, I mean, in my view, there are no completely satisfactory theories. I mean, I'm actively working on actually look for these theories, but it's not it has not reached a mature stage in which there are compelling theories that we can parameterize with a few numbers and go out and test them. I mean, DGP is the one that has come the closest.
One more question.
It's probably a naive question. In the effective theories where I take scalar and I couple it to the diagonal, taking into account the scale invariance and trace numbers and all that, I can always find solutions screen and unscreen classical theory. And they will always be unstable. You always have to add an L6 term, an LA term, and quantize it in this sense. Do you have the same problem here?
Unstable, you mean unstable against quantum corrections? Is that what you're about? Yes. Yeah, so in these theories, is always kind of assume the potential that you write down is basically the quantum effective potential, no matter where it comes from.
So the coupling constant is unknown, being unknown?
Yeah, the coupling constant is unknown. Generically, I mean, unless you have some symmetry reason that is 0, you expect the coupling to be gravitational strength. In my language, it's order 1. Alpha is of order 1.
So, okay, I think we should continue the discussion about cooking because we're running late. So let's thank Lam again.